Today, right? We're in a very good position because it looks like we're pretty much done with the chapter, right? So today I plan to, I guess, move to the next chapter. That'd be the way to go. So I can refresh your memories a little bit on 8.4. So you will just recall the formula for area that no longer will be in terms of base and height, but in terms of two sides and angle in between. So they liked to call this as a AB, for example, and then angle will be called as a C because it's always the case when the opposite side is C, then the angle is C. So the area of triangle was given to us by the formula, which is a half multiplied by the product of A and B and the sine of this angle C. And last time I tried to give you an idea why this works, and we also saw a couple of exercises, so I can do another one just to be able to make sure that we'll realize that there is nothing tricky here, but just a straightforward application of using the formula. So I can try exercise number 17. So this is our last section of chapter 8. It's 8.4. And this is on the page 571. This formula for the area, by the way, is very popular in later, not very, but you will see it again if you take calculus classes. That's why I think that's something that people should definitely be aware of. So here's angle B across the side B, and across side A, we have angle measured as A. I put a double marking to show that they're not the same. So this is kind of like wiggle marking. Because if you put the same marking, then it means that the angles are equal. So they gave us that side A was equal to 3, side C was equal to 2, and they also said that angle B is equal to 110 degrees. So this way we are going to use our formula in such a way that area now will be in terms of sides A and C. So a 1/2 product of these two sides and the sine of angle in between, and the angle will be B. And now it's really very straightforward to just plug in the formula instead of A number 3, instead of C number 2, and then sine of 110 degrees. And absolutely calculator needed to get the final answer. If somebody says, Alex, what if I don't have a calculator? Well, just get this scientific calculator, any scientific calculator that has sines, cosines in it, and that's why it's called scientific will work. I always use decimals, so you can utilize it as well because you will be on your own, and I'm sure that nobody will stop you from using whatever tool you like. So 1/2 or 0.5, I multiply by 3, multiply by 2, and also by the sine of 110. So I think that once you enter it in your calculator and get the answer, such as 2.81 and so forth, square units, right? That's a square units because it's area. Okay, what does square units mean? Well, if let's say you have a rectangle, so that's off point, but just to make sure everybody realizes, sides 2 by 3, then when you find its area, you multiply 2 by 3, right? Base times height, and you get 6. So 6 of what? Well, 6 of little squares that we call square units. Why units? They didn't tell us what measurement for the size is. They just say 5 or 3, but is that feet or that's meters or miles? We don't know. So we say units. So that's just because we're not given. So there are 6 little squares, and they called square units, or 6 of this square. So that's why square units, because all the areas measured in terms of this little squares. You don't measure it in terms of feet because area is always in terms of squares, right? So that's important to realize and not confuse it with just units, because those are ones for measuring length. If you measure in volume, then you will be using so-called cubic units. So when you measure in volume, you use those little cubes, see how many of them fit into this whatever room or whatever you're trying to measure. So again, depends. Area squares, volume cubes, or just a length in terms of those little first power units. So anyways, I'm going to move on. I'm going to go to the next chapter, because the last section here is dealing with something that we don't need, that so-called harmonic motion that comes from mechanics, and I don't think that many of you are engineering majors, and that's where this is being utilized. So we usually skip this section. And we move to the next chapter that will be giving you a very exciting story that you probably never encountered before. But before I start, I wanted to mention that next week we have a Thanksgiving. On Thursday, there is no class. And I was asked by some students, they were planning to start their holiday a little earlier. So they say, what about Tuesday? Is there going to be a class on Tuesday because we're leaving? So I told them that I can just make a formal meeting answering your questions. So I'm not going to lecture with anything new, but I can just not going to give a quiz. I understand it's a Thanksgiving week and lots of people already made plans with their families, and I don't want to be in between of you and with my trigonometry and your family plans. I understand what's more important. Absolutely, and I totally agree. But I'll get on online, and for just in case, if anyone has questions and other things, and I think that'd be fair if somebody is working on some exercises, so I'll just help with this, and if there be no questions, then you don't have to log in. I'll be there, but you don't have to, because I understand that's a holiday. So we'll continue basically after the holiday with the rest of chapter 9, because we are in a very good shape covering the material. Not many instructors get into chapter 9 actually when they teach this class, and we already have plenty of time, so I'll probably cover as much of chapter 9 as I can. And but again, I'm not going to be hurrying with that. Just want to make sure that you feel okay about this. So chapter 9 is something that we utilize in calculus 3 class. So those people that major in sciences, that will be required to take a third part of calculus, to take calc 1, calc 2, and there's calc 3, and then differential equations. And linear algebra also utilizes some of these ideas. So then it's definitely something that you need to look deeper into. And the other students that not really planning to take that course, such as calculus 3, probably not going to see any of this material anywhere again. And that's why I will be discussing this, but I guess I'm not going to be really expecting you to do all that if you don't need it. That's the message. But still, I will try to introduce it a very nice way, so it should be understandable. And maybe if you didn't plan to take more calculus classes, you will change your mind, because the stuff here is definitely exciting. We touch it a little bit in calculus 2 at the end of class also, but mostly it's for calculus 3 descriptions. So anyways, what they're talking here about is the other way to call points on the coordinate plane. So what's going on and why we need that? Well, it turns out that for trigonometric functions that all deal with a favorite little friend, unit circle, right? The rectangular coordinates, x, y coordinates, are not very, I guess, don't want to say word useful, but convenient when you try to get the description of various things, like, for example, such a relation as they say cardioid, like a heart, a cardioid, but it's coming from circular-like functions, and turns out it's nicely describable using our favorite sines or cosines or trigonometric functions. And that's why for these relations, we can produce functions in terms of those so-called polar coordinates. And to get the polar coordinates, turns out, you just need to start with some center, and you need to get a ray, which is called the direction of x-axis. And this is it. I say they put here y-axis. Well, they trying to relate this with coordinates that we're experts at, x-y coordinates. But turns out that there is totally different description of points on the plane that is called polar in terms of a pole that we call as a 0, and in terms of the positive direction of x-axis. So this way we can take any point and describe it with two things. First will be the distance, that's called radius, as if you rotated your x-axis. So that distance called r, and angle called theta. So if you know the angle that you made a rotation, and also how far from point 0 you had to go to that point that you produced, you will have so-called r comma theta description of that point on the plane. That has, again, nothing to do with x and y coordinates. It's just the angle and the distance for that, of that point from the pole, which is called 0. So that's completely different. And that's important to realize. And in this section, they trying to make you feel that everything is fine and nothing is really much different with the story of polar coordinates and what we used to deal with, such as x-y coordinates. But there is. The main difference is that it's not unique description in terms of that pair of coordinates. What does that mean? Well, you can get to the same exact point if you rotate by the angle, which is more than 360 degrees. So you can go all the way around and then get by that angle theta. I say, so Alex, why don't you then restrict your theta to be in between of 0 and 2 pi? And notice I don't include 2 pi, I just included 0, so we get a unique angle. And the answer is yes, it is possible, but remember when we solved various equations in trigonometry, then we had a division and we had to divide, and the period was involved when we divided and produced a number of solutions, and we would lose some of them. So it's not that simple. Of course, ideal situation is to exclude cases when you rotate by more than 360, or somebody could say, Alex, I also remember we could rotate the negative direction, right? So if I don't have this part, so I start there, and if I go clockwise, and I will end up at exactly at the same point as well, I say, well, that's why I keep it positive. Yes, it is, could be the case, but there is one more thing about this. The R needs to be positive in that case only as a radius, maybe equal to 0 at the pole, because in general, your R could also be negative, turns out, because that's any real number, they say, and turns out sometimes this is the case, and that's what they actually talking about in here. So the R may be negative, so I better get some example here if they made one, so I can illustrate this for you. Example 4 here. Part B. Let me clear this stuff on the right side. Let me do 4B here. They will move to the right side then. So if you have a point in your polar coordinates that is described the following way, your R is -4, and your angle theta is -π/4. Turns out that if I take the angle theta, which is -π/4, I say, Alex, why did you put this XY axis? Kinda automatically, because technically it's not really what's happening with this polar coordinates. So I produce rotation by -π/4, so I go clockwise direction by like 45 degrees. But what should I do with the R being negative? Well, it turns out that instead of going 4 units along this angle, I must take this 4 units opposite way. So my point is actually going to be right here. So this is the pair that they want us to produce. And one can say, so why didn't you just put 4 positive, and angle looks like will be 3 of those π/4? That'd be the same exact point, but that's a different description with both R and theta positive, so they could fall into this region. But historically, they don't use this. And that's what they're trying to explain, that there is no unique representative for the pair R and theta, even though you have just a point on the plane of coordinates. Let me see, so why is this being done? Why would they care about it? Well, it turns out that actually complex valued functions, or they call analytic functions, enable us to mathematically describe fourth dimension. So it's not just for plane of coordinates, because it really kind of doesn't really make sense why you use it, unless you just look at those like heart-like little graphs. But it very well describes 4-dimensional objects that we cannot imagine. So turns out we're thinking in 3 dimensions, but the functions that deal with XY plane and send it to another XY planes, it's like 2 dimension to 2 dimensions, so it's 4. We can't even graph, but we can somehow think of them using the ideas of this complex, I don't want to say complex numbers, actually, that's where it's coming to, but the polar coordinates that help us to work with those functions. So it actually opens the door into various areas of mathematics, and this is just being introduced, so it's not that simple, and there are big reasons why they actually utilizing all that. And again, for people that be interested in describing things and taking more math classes, it could be definitely useful in their future studies. So basically, that's pretty much all it is. And now I can also relate this to favorite XY plane. So if you have points on XY plane, so for convenience, I'll take the first quadrant. And if I consider my favorite unit circle, so if circle is radius 1, and I remember that the coordinates of this point on the unit circle will be cosine of angle theta. That's angle theta. And then sine of angle theta, right? X and Y coordinates. Then, of course, point does not have to be on the circle of radius 1. It could be any radius r. And then we get a similar triangles idea. So we already talked about this, but just refreshing your memories. So this is going to be like radius r here, the new radius. So the question is, what about the coordinates of that point here on the circle? And the answer is, it's all r times bigger. So for the x coordinate, it will be r multiplied by cosine theta. And for the y coordinate, it'll be radius r multiplied by sine theta. I think that's what they discussed in the previous page. I just went through them and saw these little formulas that we already utilized before. So it turns out these are key formulas. X is going to be r cosine and y is going to be r sine. And that's actually idea why, because of, again, similarity of those triangles. So I guess I'm going to do some exercises now to make sure that we get used to this a little by little, and that'd be the plan. So I can go to the end of the section as usual and find some nice little problems. I will continue with this section later. I don't plan to do the whole thing because it has lots of ideas here that I think you should not hurry with, just to, again, get used to. So the exercise, say number 9, that says match each point in polar coordinates with A, B, C on the graph. Okay, so in other words, I just want to make a picture of this point. So I can do that. I can get an angle theta. So R is 2, and angle theta is negative 11 pi over 6. So I guess the only similarity with XY plane is they write, instead of first and second position, R and theta. But that's just totally different story. So 11 pi over 6, I think, will be here, because if this is angle pi over 6, right? If I divide this by 3 pieces, and then 3 and 3 and so forth. Then 11 pi's over 6 will be ended up at the exact same angle. So if you just rotate by negative 11 pi over 6. And then the value of r is 2, so I just go along this by 2 units, and that's where my point was these coordinates. Let me write them again. 2 for the radius and negative 11 pi over 6 for the angle will appear. So this is my pair, and looks like this is point A, right? So we just did the match 9 with A, just like that. So it looks like in all these exercises, you just want to match the point with either A, B, or C, or D. Okay, so how about if I try to plot exercise number 19 in the polar coordinates? And again, I don't want to write this as XY pair because it may be easily confused. I just say that R is -2 and theta is equal to 0. So I think this way we can better visualize what's going on. So theta is equal to 0 means that we're on the x-axis, but r is negative, so we actually have to go 2 units in this direction. So our point is here. When you say, Alex, in xy coordinates, it's also same pair. Yes, it happened to be, but it's not always going to be the case. I think when angle is 0, that's the only possibility, yes. But if angle is not 0, then definitely it's not the same. So making picture, again, just be aware that it's not xy, it's a pair. X is dealing with this distance to the pole, and y is not a y, it's angle, so it's totally different. So how about the exercises like number 37? So I'm selecting one problem from each group of exercises. It looks like first 2 groups are pretty much the same. So what about number 37? They gave us a -3, -pi over 4. Again, that's a point in the polar coordinates. So what they want is to plot each point and then other coordinates for which, so we want to then produce 2 more parts, or actually 3 more parts. So first of all, they want me to plot this point. Okay, I can do this. -pi over 4 is my angle, so we'll always start with the angle. So I'm going to put -pi over 4 here. I just put this marking because now I have to decide what about r, right? This is my r, this is my theta. Well, looks like we have to go the opposite direction by 3 units to get to this point, because this is going to be going the opposite since it's -3. Okay, so what about part A? What do they want here? I guess they want us just to practice, to get used to the ideas of the other way to describe the same pair. So for example, if they want you to get a negative angle, but r will be positive. Well, if r is positive, then the angle should be here, right? Negative. And looks like this will be taking this pi over 4 once, twice, 3, 4, 5 times. -5 pi over 4. So notice that description changes if you decide to get the different one of the coordinates. That's worth to think about. I think over weekend it'd be good if you redo the same problems, and if something does not work, as I said, on Tuesday we can do this together, or maybe you will practice more and find something else you want me to do. I think today I'll just do problems on this page and this group of exercises, and then we'll move on to another part of the section later, maybe after Thanksgiving. So next part B here, that says, how about now if angle is positive, but R is still negative? So how can I get to the negative R, which is going to be -3, right? Because we're still describing the same point. But we have to go from this angle, right? From that direction, actually. But how can I make it be positive instead of -π/4? Well, it looks like I need to go the opposite way, like that, right? So in the part B, it looks like I have -3 for the radius, but I went not by -π/4, but looks like by 7 of these pi's over 4, right? We already know this. 1, 2, 3, 4, 5, 6, 7, if you go counterclockwise. And that's a part B. Again, maybe tomorrow you can get a piece of paper and try to reproduce this yourself. Because if you be able to do it once, it's good enough. You will do all these exercises and that'll be pretty straightforward. But you really want to try it once, and that way I think you will get used to this right away. So let me do part C now. The part C says, now you want to have between 2π and 4π and t is positive. Well, it looks like we had one case when t was positive, it was part A, but they wanted negative. So now they want to rotate a little bit more. I think I want to make another picture of this because it's already too messy. So my point is here, let me keep it red. So I went 3 units here, right? So they want me to have a +3. They say, why positive? Well, they say here, R is greater than 0. So it'd be +3. But for the angle, they want to rotate more than by 2π. So more than full rotation. So they want to go full rotation, right? And then some more here. So how much more? Well, looks like I need to have 2π added with 1, 2, 3 of these pi's over 4. Okay, so if you want to write everything in terms of one single fraction, you can give it same denominator 4. So instead of 2π, I can put 8 over 4, which is 2π. So it'd be 8π over 4 plus 3π over 4. So when I add, I get 11π over 4. And that'd be an angle in between of 2π and 4π. Why do we need that? I think they just made it up for practice. I don't think you will use it anywhere, but it's just to make you feel comfortable doing these problems. I say, Alex is kind of, yeah, I don't think I will give you a quiz today because it's just very new stuff. I think you need to get around these a little bit better. So why don't I just do one more exercise and instead of quiz, and that should be good enough. We do 39. There's one here on the bottom. So polar coordinates given. What about rectangular coordinates? Exercise 39. Again, I don't like this way to describe points. I like to say r is 3, and then theta is pi over 2, right? So what about rectangular coordinates? Well, they're here. So x and y, x is r cosine theta, and y is r sine theta. So it turns out when you have formulas, you don't really care what numbers they gave you, just plug numbers in. So you get 3 times cosine pi over 2, so you may not even make a picture, 3. You could just put numbers in your formulas, basically, that's what it is. Because sometimes it's kind of hard to get it intuitively. Well, for this exercise, I don't think it's hard. For this exercise, I think it's pretty straightforward, but still, if you recall angle pi over 2, then its cosine is going to be a x coordinate, which is 0, and sine is 1, right? So instead of cosine, I put 0. Instead of sine, I put 1. Pi over 2, or pi over 4. I think I'm getting tired. So it's 3. So we actually have point with coordinates x equal to 0 and 3 for y. So it's really a point here with coordinates 0, 3. Let's see. So how is it related with that? You don't have to think of this as x, y. That's why I'm saying it's totally different description for this case. So it's worth to notice that if you actually have angle pi over 2, which is 90 degrees angle, right? And then if you go 3 steps from your pole in that same direction, you ended up at that same place. So I got the answer. So I guess I'm going to stop at this stage and let you relax a little bit. I know it's a weekend coming, end of semester, and well, as I said, I'm pretty happy with the results of students in class, and I think next week you can take it easy because of big holiday, and then after the holiday we're gonna do a little bit more of this, because after the holiday, how many weeks we have? We have 1 week that ends at the beginning of December, and then another week. So we're gonna have 2 weeks and then the final exam. So basically, like 3 more classes, because before the final we're gonna do a review. So that'd be the review. So 3 more classes. So in 3 more classes, I'm sure we're gonna get far enough in this chapter. And as I said, I'm not gonna hurry because we wanna really get used to this new description of polar coordinates and understand they're totally different with x-y coordinates, because once you get used to it, well, the next sections will be pretty straightforward. And that's why I don't hurry at this beginning. It's very important that we all get to start feel comfortable about this different way to describe points on a plane. And it's no longer XY plane. That's the, I think, main barrier and mind breaker that some people need to somehow start to realize. So I'm gonna stop at this stage and see if you have any questions or any ideas, if any